Before we begin, a few housekeeping points. We are not expecting a fire alarm during today's lecture, so if the alarm sounds, please treat this as real. The fire exits can be found at the back of the lecture theatre and to the side of the stage here. Our muster point is located outside the Royal Astronomical Society in the courtyard. If you have any questions or require any assistance, please look for staff who are identifiable with the yellow lanyards. There will be a Q&A section after the talk today. For those of you joining us in person, please raise your hand if you would like to ask a question, and someone will come around with a microphone so that those online can hear. And for our virtual attendees, you will be able to submit your questions via the Q&A function, and we will read out the questions for you. There will be a drinks reception taking place after the talk in the lower library, so for those of you in the room, please do join us after the talk if you can. We are proud to partner with KSAT, who are supporting our public lecture programme throughout 2025. The collaboration enables us to share cutting-edge insights and geoscientific discoveries with public audiences, broadening our reach and amplifying the impact of our science programme. Elias completed his geology degree at Imperial College London and a master's in geochemistry at the University of Copenhagen, where he developed a passion for Precambrian geology. In 2021, he began a PhD at University College London under Professor Graham Shields, focusing on Snowball Earth and conducting fieldwork on Scotland's Garvellach Islands. His research gained international attention in 2024, and he was named the Geological Society Early Career Geologist of the Year in 2025.
Thanks very much. And yeah, I just want to start by saying thank you to everyone for coming and listening to me talk for an hour today. It's a little bit overwhelming, but yeah, thanks for that. And thanks to the Geological Society for hosting and the Early Career Network for the invitation. What they've invited me here to talk to you guys about today is actually shining in the background of this photo there. That is Costa del Scotland, would you believe it? It does actually look like that sometimes. But more specifically, that is the Garvellach Islands, where I've been doing my PhD for the last 4 years. And the reason that I want to talk to you guys about that today, and the reason why I've been working there today, across the last 4 years, is that they record a rare record of what is known as Snowball Earth. This tiny uninhabited chain of islands off the west coast of Scotland preserve a very unique piece of the geological record. And before I go on, I must acknowledge the person in the forefront of the foreground of this photo. That is a man named Anthony Spencer. Tony did his PhD on these islands in the 60s. And there he is, 80-something-year-old, still trudging around these uninhabited islands. And that's been a massive inspiration for me during my PhD. And should be a massive inspiration for everyone else at the age of 80, still doing great scientific work. So this clicker does work? Doesn't work. Oh, it does work. So yeah, just the presentation outline, what I'm going to be speaking to you guys about today. It's about 45 minutes long, so hopefully you can bear with me for that long. But I'm going to first introduce the concept of Snowball Earth, I promise. There is no computer. Just click the... There we go. So first I'm going to talk about what is Snowball Earth. Then I'm going to introduce the problem. I think someone is controlling it up there. I don't know whether this laser pointer is working. Is there a way I can override it? Here? No. So I'm going to talk about a problem within Snowball Earth science, something that has really hindered us for the last kind of 20 years for progressing the science forward. And then I'm going to talk about the unique geology of those Garvellach Islands that was in the picture that you guys saw before, and why the unique geology of the Garvellachs potentially fills and satisfies the hole that problem I will introduce in point 2. And then the next point that I'm going to introduce... Hello? Oh. Is I'm going to show some new geochronological age constraints that I got during my PhD. Oh, the clicker works, perfect. And then talk about what that means for the geological timescale. So as I said, I'm just going to introduce Snowball Earth for those. Sorry if it's a revision lesson for some. But Earth has three main climate states. We have a greenhouse Earth, which will pop up any moment, like that. This is where there is no ice on land or at the poles. We have an icehouse Earth. It's just a picture of the Earth with ice on it, if you can imagine that. There it is, where there is ice at the poles and there is ice on land, and we're in an icehouse Earth today. So Earth fluctuates between these two climate states at reasonably regular intervals throughout Earth history. And that's because it has a number of self-regulating feedbacks which prevent it from becoming too hot or too cold. Which is why this third climate state is a little bit strange, and that is the Snowball Earth climate state. That describes a climate state where ice covers the entire planet, all the way from the poles down to the equator. Now, we have to go all the way back in our geological record to... Is this touchscreen? All the way back in our geological record to... the Cryogenian, which is hopefully going to be highlighted in a second. I've got too many. There we go. All the way back to the Neoproterozoic, and in particular the Cryogenian period there, which lasts from around 720 to 735 million years ago. That's when we last saw our Snowball Earth climate state. So if we zoom in on that period, it's important to note that the Cryogenian is made up of two distinct Snowball Earth intervals, and this becomes important as my talk will progress. It's made up of the older Sturtian glaciation, which lasts from around 720 million years to around 660 million years, so it's a 58 million year or so glaciation. Then there's a non-glacial interval, and then we have the younger Marinoan Snowball Earth glacial interval, which is less well constrained. Its onset, 650 to 640 MA, and then terminates at 635 million years ago. And the Snowball Earth climate states, besides from being these kind of rare, strange climate states which shouldn't really happen on a planet like Earth, there seem to be a pivotal time in Earth history. This is a phylogenetic tree, and if you look at where you could trace a lot of these trees back to, it's actually within the Cryogenian period and within these Snowball Earth time periods. So the roots of a lot of different animal crown groups and the first appearance of them seem to be happening during Snowball Earth. So these major glaciations in the Cryogenian period seem to be quite important for Earth's evolution. So, a history of the Snowball Earth. How did we get to the point where we knew about these glaciations? Well, all the way back in the 1930s and 40s, geologists started recognising the global distribution of Precambrian glacial deposits on nearly every continent. And they started piecing together that this seemed to be almost too common in the record before life, in the Precambrian record. We now know that Snowball Earth deposits are present on every continent on Earth. So you see here the coverage of the Sturtian deposits and the Marinoan there. So, but fast forward another 30, 40 years, and we have the publication of Anthony Spencer's memoir. Rather serendipitously, he is underneath the tick there on the photo. But as I said, he did his PhD on these islands in the 60s, and the Geological Society agreed to publish his work as a memoir called The Late Precambrian Glaciation in Scotland. Now, a lot of these glacial deposits, it was debated whether they were actually glacial in origin, and a lot of Tony's observations all the way back in the 60s, it kind of confirmed that these deposits that he was seeing were definitely glacial in origin, and his observations then set a kind of a standard by which other people then set themselves to. So I put that in because it's quite a pivotal piece of work in Snowball Earth history. But it wasn't until the 90s that we first heard the term Snowball Earth, and it was this man, Joe Kirschvink. Now, Joe Kirschvink was interested in where continents were in the past, and what Joe recognised is that some of these glacial deposits that we were finding in the Precambrian seemed to be deposited at the equator. Now, because of the temperature gradient of the Earth, if you have ice at the equator at low altitudes, then you must have ice everywhere on Earth. And that's because of this process, this forcing called albedo. And albedo is the reflective forcing of ice. So Joe coined the term Snowball Earth because he basically couldn't see any other way theoretically that you could have ice at the equator and not cover the entire planet. But we're obviously not in a Snowball Earth today. So Joe had to come up with some way, a mechanism to get out of a Snowball Earth, because if you've got the entire planet covered in ice, you've got this massive albedo forcing, the reflective forcing of sunlight. When does that become overwhelmed that it all melts back? Well, the dynamics of Earth isn't going to stop, and carbon dioxide is still going to build up in the atmosphere, and it's going to build up to such a threshold that the atmosphere is going to become so hot, and you're going to get a major deglaciation event. But unfortunately for Joe, his work was hidden in a 2-page document in a very large volume. So people didn't really take it seriously. And it was very theoretical until this man, Paul Hoffman, came along. And Paul Hoffman took a lot of Joe's ideas and applied them and looked in the rock record. So this is in the late 90s. There's Paul Hoffman standing on one of these Snowball Earth deposits, pointing at what is called a cap carbonate, because Joe had set up the stage nicely theoretically. However, this needed testing with the geological record. And what Paul is pointing at there is what's known as a cap carbonate. Now, if you had this massive increase in CO2 during Snowball Earth, and essentially deglaciation would only happen once you reached a critical threshold, well, you'd have very quick and very rapid deglaciation. And if you had rapid deglaciation and rapid warming after these Snowball Earth intervals, you're going to have a lot of alkalinity driven into the ocean, the temperatures are going to soar, and you're going to deposit a lot of carbonate. So Paul brought together a lot of the ideas that had come before him of Snowball Earth, and the Snowball Earth hypothesis really started to snowball. That was too big a laugh, but thank you. And we had another issue, and that issue was that we didn't know how old these deposits were in particular. And a lot of Paul's students and others spent the next kind of 20 or so years dating these deposits. Geochronological techniques came on leaps and bounds, and all these geochronological constraints are on this plot here. And what you can hopefully see is that they confirm that these glacial intervals were globally synchronous events, both the onset of glaciation and deglaciation, and we have those two discrete glacial intervals, the Sturtian and the Marinoan. So they really put a nail in an arrow in the bow, let's use that phrase, of Paul Hoffman's Snowball Earth hypothesis. So the Cryogenian Subcommission and my former PhD supervisor, who was chair of the subcommission at the time, because of these new geochronological constraints, they set about changing the geological timescale. And the Cryogenian period, which was previously set at around, the base was set around 850 MA, they moved that up more in line with the improved geochronology, and it was set at 720 in 2016. And all we're waiting for now is the formal ratification of that in the geological record in the form of a GSSP. So During my PhD and for my PhD topic, I was trying to understand how and why Earth got into this enigmatic and rare climate state. But very early on, I encountered a problem, and that problem was glaciers are incredibly erosive agents. You only have to go to a recently glaciated environment to see that these things plough through nearly everything in sight. And that's no different in the geological record. These are examples of Precambrian Snowball Earth deposits. And you see here they're made up of large clasts and ground up rock flour that have been ground up from the bedrock below and then deposited. And I'd always like to try and include this image here. That is a 40-metre tall by about 100-metre wide carbonate raft that an ice sheet has literally plucked up and transported and then folded. So you see the sheer power of these kilometre-thick ice sheets. That's a massive issue for us if we're trying to get at this problem of how and why we ended up in a Snowball Earth, because the record preceding Snowball Earth has pretty much entirely been removed by glacial erosion. That late Tonian period that we're trying to look at, we're trying to probe, we're trying to test our hypothesis, is missing from the record. I'm going to take you on a short field trip to the Garvellach Islands now, and somewhere where we hope we can argue that this ubiquitous erosion event hasn't occurred on these islands off the coast of Scotland. So the Garvellachs are situated off the west coast of Scotland. They're a chain of 4 uninhabited islands. They're an incredibly beautiful place to do field work, and I feel very lucky that I've spent a large part of the last 4 years there. More broadly speaking, geologically, they form a small part of what is known as the Dalradian supergroup. Some people in the room might be familiar with this supergroup, but it's a huge package of rock in Scotland that's bound by the Highland Boundary Fault to the south and the Great Glen Fault to the north. It was deposited between the Tonian and Ordovician periods, and it's made up of 6 groups, and it's about 10-15 kilometres thick. But the Garvellachs there, does the laser work? Oh yeah. The Garvellachs there is the star, that's where we're focused on today. And this is what the Garvellachs looks like as a geological map. This is oriented north here, pointing to the top of the screen, so I'll just spin it round and make it a little bit bigger. Yeah, ooh. And this is a geological map of the Garvellach Islands. The orange colour, which covers most of the islands, is a glacial formation. It's one of these Snowball Earth deposits called the Portascaig Formation. And it's a very famous deposit. Globally, people come to these islands to look at that all the time. But I'm particularly interested in what's in this red box here, and that's beneath this Snowball Earth deposit. And that's the Garvellach Formation. We have some carbonate preserved just on the northeast of the island. We also have some more recent history, which is quite interesting. We have these beehive monasteries that are on this island called Aileach an Niamh, and they're some of the oldest beehive monasteries preserved today. It's where Columba used to go in the 6th century to take his retreats. So they have modern history as well as ancient history. So that glacial formation, the Portascaig Formation, this famous Snowball Earth deposit, it's about 1.1 kilometres thick. We divide it up into members, which is then divided up into different discrete diamictite beds. And we have some other rocks in there as well. It looks something like this in the outcrop. This mess of kind of rock flour and large clasts of all different lithologies. And we see deposits of it across the whole Dalradian supergroup, stretching from the northeast of Scotland all down into Donegal and Connemara in Ireland, these red dots. But the best exposed and best preserved and thickest Portascaig Formation we see are in the Garvellachs and Islay. But as I said, I'm interested in what's beneath here, the Garvellach Formation, preserved on the Garvellach Islands. But before we go on, I can't not show some field photographs of the Portascaig Formation, as this is a 700 million year old glacial formation, and the fact that it preserves some of these features still today I think is quite remarkable. So we have here a modern day example of what the process looks like, and then an outcrop picture of the Garvellachs. And we have these things called drop stones, which are ice rafted debris, so debris taken by an iceberg, and then when it melts, it drops into the sediment below, and you see it nicely preserved there. We have these things called ice wedges, which form during freeze-thaw cycles. So when you freeze, you have the contraction of the ground, and sand blows into them, and then they form these nice polygonal shapes here. We also have things like ice push structures, boulder trains, frost-shattered clasts. It's really quite a remarkable formation geologically. But as I said, I'm interested in the Garvellach formation, the carbonate beneath the Port Escape formation. And there we go. It's around 75 metres thick of what we have exposed, and it all dips around 30 degrees to the southeast. And what we're trying to argue for is that we have continuous sedimentation into the Port Escape formation with little to no erosion. We have a complete record into Snowball Earth, which would make it unique in the global record. So this is what the Garvellach formation looks like stratigraphically. It's about 70 metres thick, and we have 3 overall broad facies associations. We have a limestone and dolostone facies association that has some stromatolite horizons in it, before we move to some siltstones. And then we get this dolostone facies association, and this is where we start seeing what we argue to be early signs of ice. So as well as not seeing an erosional unconformity within the section, we also see sedimentological evidence for a gradual transition into a cold climate. So, as you saw just at the bottom of that stratigraphic log, we have these things called stromatolites. These are microbial mats. And these typically form in warm tropical seas. And this isn't unexpected for Scotland, as Scotland at the time was situated somewhere close to the equator. So this is quite typical of deposits in these regions. But this is kind of 50 or so metres below that unambiguous glaciation. We have some tropical oceans. So this is quite a remarkable thing, and this is why I include it, as we have this transition from a warm climate into a cold climate, all within 70 metres of succession. But it's really when we get up to that dolostone facies association that we start to see these things that we argue to be early signs of ice. And the first thing that we see are these things that we argue to be ice rafted debris or dropstones. That are these things, as you saw on the picture before, they're carried by floating ice, and then when the ice melts, it drops them into the sediment below. Here, under a microscope, you can see that they pierce laminae, and this is actually a frozen piece of till that has been frozen and then transported and dropped into the sediment. We see periglacial emergence horizons. These are when the ground freezes and brecciates like this, and you see there's a definite gradient there, with increases in brecciation towards the top. We also see gypsum pseudomorphs. Now, gypsum pseudomorphs, gypsum is an evaporitic mineral, it's a calcium sulfate, and it forms in warm, arid environments. People think it forms in warm, arid environments, but it's actually the aridity that is important, and the most arid place on Earth today is Antarctica. And actually people have looked into the ice sheets on Antarctica and they find gypsum precipitating there. So we use these 3 pieces of evidence in conjunction to say that we see an early onset of a cold climate before we get the definitive glaciation of the Port Escape formation, which are these diamictites we see here. So hopefully you can see we've got a nice sedimentological record of a transition into a Snowball Earth deposit. However, in Scotland we have a different issue, and our issue is we don't know when these rocks were deposited. Hopefully you can remember that we have 2 Snowball Earth intervals, and our issue with the Port Escape formation is we don't know whether it belongs to the Sturtian Snowball Earth interval or the younger Marinoan one. This is the Dalradian supergroup on its side here. The geochronological constraints, how old we know the rocks are here. We have a lower limit here of 840 million years, which defines is the age of the underlying basement. Then come kind of 10, 15 kilometres up in the section before we have our next geochronological horizon, and that is a 600 million year old ash bed. We have the Portishead Formation slap bang in the middle of them. Unfortunately, we only have one glacial deposit within the whole Dalradian, so it really is tough to attribute it to either the Sturtian or the Marinoan. We have, 240 million years of Earth history and 15 or so kilometres of stratigraphy, which is undated. So again, that means the Portishead Formation, this glacial, could either be the Sturtian or it could be the Marinoan. How do we test that? Well, we have no ash beds, we have no fossils, we have no igneous bodies for cross-cutting relationships. So we're a little bit stumped. We do have some indirect evidence. This is a bit of a scary figure, I'm sorry, I won't delve into it too much. But we have a stratigraphic framework within the Irish Dalradian of 3 glacial intervals, the oldest of which being the Portishead Formation there, which would suggest that the Portishead Formation was Sturtian in age. We have these carbon isotope excursions here, which we can match with other localities worldwide, and by matching this pattern of carbon isotope excursions, it seems to also suggest that the Portishead Formation is Sturtian. We have iron formation in the Portishead Formation, and this is only known in Sturtian deposits worldwide. We don't see iron formation in any Marinoan deposits. The strontium isotopes that we also use to try and anchor ourselves in time suggest that we have a Sturtian deposit. And we also have some carbonate fabrics in these rocks underlying the Portishead Formation, which are indicative of pre-cryogenian sediment. So we have all this indirect evidence, but we don't have any age control. We don't have any numbers, and this is a massive issue. So what I did during my PhD, I collected 11 sandstone samples from throughout the Portishead Formation and underlying Garvellach Formation. I extracted these minerals called zircons from each sample, and I measured the uranium and lead isotope composition on a laser ablation mass spectrometer at UCL. Now, zircons are this amazing geochronometer, this amazing mineral that forms in magma chambers. And when it crystallizes in a magma chamber, it incorporates an amount of uranium, but not much lead. And over time, some of this uranium, it decays to lead at a known rate. So what we can do is we can measure the uranium and lead isotope composition of this mineral, and it will give you a crystallization age of when that mineral crystallized. Now, maybe some of you are thinking, okay, that's all well and good, but you haven't been looking at igneous rocks. You haven't been trying to date a Pluton or something like this, or an ash bed. But we use this simple rule here that a sandstone cannot be older than its youngest grain. So we used that rule, and we fired a load of lasers at a load of these minerals here, and the results were quite remarkable. What we found is we had 8 samples which yielded zircons with ages that fell within the constraints of the Sturtian glaciation. We found no zircons from below the Portishead Formation that had an age younger than the globally accepted onset. The uppermost sample here, which was taken from just above the last glacial deposit, was in strong agreement with a 660 million year deglaciation. And we also see this nice trend here in the ages, which suggests the zircons could be close to the depositional age. So if we combine these new age constraints with that amazing sedimentological transition that we have on the Garvellachs, we have perhaps the most complete record of Sturtian glaciation known on Earth. So just to recap that, now we can more confidently say that we have the Garvellach Formation in the late Estonian, and we have the Portishead Formation deposited in the earliest Cryogenian. But who cares? I published these results in the Journal of the Geological Society late last year, and it turns out I wasn't the only one who was excited by these results. It even landed me a very nerve-wracking interview on BBC World News. But actually, why was this? Why was this a big story that the press got hold of? Well, hopefully the keen-eyed amongst you can see that is me. maybe the more keen-eyed amongst you can see that it's me holding a rock hammer. But I know there's a few people in the audience that can see that that is me holding a rock hammer, holding a carrot. Now, I don't know how many geologists there are in the room, but I've been doing geology now for about 10 years. And it's pretty tough to convince your family and friends that you're looking at rocks is a worthwhile endeavour. You're usually the butt of most jokes, right? And perhaps fair enough. But I published these results, and the press got hold of the story, and I was excited. I thought this might be the time that my family and friends start taking geology seriously. Oh, this is really good. And this is the picture that BBC decided to use for their main article. So, thanks, BBC. And they put this caption with it. The discovery was made by Elias Rugen, here pretending to hammer in a coveted golden spike. For now, he's making do with a carrot. Again, cheers, BBC. But I've come to quite like this photo, not least because my nieces find it hilarious and has got me the nickname Carrot Boy amongst the family. But it's what it symbolises. And it's this point in the caption, this coveted golden spike, that is why I think it actually symbolises what the research means quite well. So, the golden spike. In 1869, they completed the railroad track connecting the east of the United States to the west of the United States. And when they did that, when the final bit of the track connected, they decided to have a ceremony. And during that ceremony, the last spike that they hammered in a gold spike into their track. And it looked something like this. You can see it now at Princeton University. And that golden spike, that completion of the track, what that symbolised, well, you could now get from West United States to East United States, so it symbolised a spatial transition, but you could also cross time zones now in the United States. So it was a symbol of a transition in space and time. And that's what we do with our geological record. Hopefully you can see here at the base of each period and stage, we have these golden spikes. These are known as GSSPs, or Global Strata Type Section and Points. And this is what we divide our geological record into. The Dalradian is a perfect example of why we don't use absolute ages. It's a massive misconception in geology that we know how old every rock that we pick up is. We have 240 million years of history in the Dalradian, which is undated. So what we use events, and we use events such as mass extinctions or climatic events to divide our geological timescale. But we need a way of defining that, and we use these GSSPs. They're a rock-based division of geological time, and it allows the start of each geological period to be correlated globally. And where we place these GSSPs is also important because that place needs to represent that transition as best possible. So we place it at the archetypal section of what we consider it to mean to move from one geological period into the next. So perhaps one of the most famous transition in Earth history is the KPG boundary, the demise of the dinosaurs. And this is placed in Tunisia. And throughout the geological record, most golden spikes are placed based on changes in fossils. And this is slightly different, but we do see the disappearance of 90% of foram species. We get this clay-rich layer, we get this iridium spike, we get a number of different attributes that come together, and Tunisia just so happens to be the best place that you can see this. And even as far back as the basal Cambrian, we're still defining things based on fossils. The base of the Cambrian is, and the GSSP is placed in a mistaken point in northwest Canada, and that's defined based on the first appearance of this trace fossil called Trectichnus pedum. And this is supposed to symbolise an increase in complexity of animal motility. Moving back in our geological record, the most recent GSSP to be ratified was in 2004, and that's the basal Ediacaran. Now, this was the first GSSP to be ratified based on a chemical and oceanographic event only. And it's placed in the Nuckalina Formation in South Australia, and it's placed in one of those capped carbonates that Paul Hoffman was pointing at the start of the presentation. So next in line we have the cryogenium. But we have to decide first on some attributes, some requirements that we require our basal cryogenian candidate section to have. And Graham Shields, who was the head of the subcommission at the time, put together these requirements. You need simple things like good exposure, continuous sedimentation, the absence of dramatic alteration. You will also need other stratigraphic methods such as isotope stratigraphy and other requirements like that it's going to last, it's going to be permanent, you've got good accessibility to the section, free access for researchers. And Graham, with that, he put together a list of these candidate sections, potential places around the world that we could look to place this basal cryogenian GSSP. But what became apparent is that some of these requirements are more important than others, and this transitional contact interglacial seems to be one of the more important attributes. You simply can't put a GSSP somewhere where you have an unknown amount of time missing in the record. They wouldn't have placed that golden spike in the train tracks if the preceding 100 to 200 metres of tracks was missing. And that's no different for our geological record. And unfortunately, because of that glacial erosion phenomena that I introduced early on, that rules out nearly all of our candidate sections. And we're left with the Garvellach Formation in southwest Scotland and the Tambien Group in northern Ethiopia. Now, unfortunately for northern Ethiopia, accessibility has been a massive issue across the last 10 years because of civil unrest there, and the research just hasn't yet been done. So that's why I've been working across the last 4 years to propose the Garvellach Formation on the Garvellachs to be the leading candidate for the basal cryogenian GSSP. And how do we go about this? Well, the cryogenian has a subcommission of people who work for the International Commission on Stratigraphy. There's approximately 20 voting members. The island has been visited 3 times, twice in the last 4 years, co-led trips with myself. And the proposals is currently being written and will be submitted in February 2026, and members will then vote in May 2026. And we're hoping that the Garvellachs are a leading candidate, and hopefully I've shown to you today why that is. And with that, I'm going to leave you with my favourite article, press article, and hopefully you've learned enough to realise why I like this one so much. Golden spike discovered in rock formation reveals when Earth became a snowball. And then we have to see the golden carrot one more time. But thank you very much, and I'm happy to take any questions. Do I just point at people?
Thank you very much. Really good presentation. Has there any work been done on the rafts? And has there been any determination on the raft in placement mechanics?
Yeah. For those that don't know, rafts are these kind of larger blocks that have been plucked up by these glaciers and transported. I was too quick to finish, but I should just acknowledge these 3 people here, Tony Spencer, Ian Fairchild, and my supervisor, Graham Shields, who've been helping me. But the reason I do that is because Tony and Ian are currently writing a revamp of Tony's 71 memoir. And within that, they've been spending the last kind of 15 or so years doing work on things such as the rafts. So looking at them kind of from a structural point of view, how did the ice sheets potentially get them to where they are in situ now? And we've also done some geochemistry on the rafts to try and place them in the pre-glacial record for where they've come from. Does that answer your question?
Hello. Hi. Thank you very much for your presentation. That's very interesting. Oh, I have a quick question. So you may have already answered to this question. If so, my apologies. But I was wondering, how did the Garvellach Islands were protected from the erosions? Is there a geological reasons? And also about the Ethiopian formation as well. How was that protected from the erosions that seems to have influenced everywhere else?
Yeah, I mean, that's a great question. Perhaps I didn't mention it. It's because, in short, I don't really know. And no, we don't really know, but it is strange because if you have this massive global glaciation, you're going to have predicted sea level drop of 200 to 400 metres. So therefore, an unconformity and an erosion is almost an inevitability. There's a few options of what could be happening at this section specifically. There's a potential that this is actually on the flanks of a valley, so all the erosion is kind of concentrated in the valley floor, and then as that gets filled up with sediment, then you have kind of a protected area that's being deposited kind of more slowly than the valley floor, which is being eroded. Or you could just be that the basin subsidence is actually quite quick in the Dalradian, such that you have a rapidly subsiding basin that's basically kind of escaping, running away from the ice, if you like, and escaping that erosional phenomena. So as you get sea level drop, you're also getting an increase in accommodation from basin subsidence. But yeah, in short, it's a really good question, and one that I hope we can get at in the future.
So we have a question from Jonathan online. They say, you mentioned that CO2 levels continue to rise during snowball periods. Is that because of ongoing igneous activity releasing CO2, or is there another reason?
Yeah, so Snowball Earth wouldn't halt volcanic activity. The dynamics of Earth would still be spewing out volcanic eruptions, and carbon dioxide is one of the gases that it'll still be spewing out. But essentially, you're going to be blocking the reaction between carbon dioxide and the crust and silicate minerals, and this is what kind of controls temperature over long time periods. And if you don't have any CO2 drawn down through the reaction with silicate minerals, then CO2 is just going to build and build and build to a critical threshold, whereby you have really intense warming and intense meltback.
I have another question, sorry. Duncan has asked, has your work removed the stumbling... Norman, sorry, has asked, has your work removed the stumbling block of poor radiometric control marked against the Garvellachs in Graham Shields' table?
Yes, so I wouldn't say it's fully removed that kind of ambiguity. It's definitely strengthened the case for the Portishead Formation being a Sturtian deposit rather than a Marinoan. And we do have some numbers in the deposit, which is nice now. We have an updated version of that table, which we are submitting along with our proposal in February. So yeah, that's one of the kind of columns that's changed.
I'm Susan Graves. Thank you so much for such an interesting lecture. I hope you don't mind my naivety, but in the lab, it's possible with an inorganic polymer, such as a dioctahedral mineral, to make a border between the carbonate and the actual polymer, whatever you do, according to the method. So it was just interesting to see how you showed the border, like the curved line between the carbonate and whatever else was there, maybe basalt, I don't know. Do you find that a lot? Is this your work, or is it just a one-off? And thank you for listening.
No, thanks for the question. I don't recall the photo that you're referring to, but we don't. The Garvellach formation isn't very organic rich at all. So we don't have many organics. It's pretty much either pure carbonate or we have some siliciclastic material in there as well. But organic material, even in the kind of finer sediments where you'd potentially expect organics to be preserved, you don't see much organic carbon now.
Thank you.
So we have another question from online. Duncan has asked, what biota is present in your sections? Trace fossils, paleomorphs?
We are actually before the time of trace fossils, so we don't have any moving animals all the way back in the Cryogenian. So, in short, there aren't any fossils. The only fossils that you would find around this time are microfossils. We have things like vase-shaped microfossils and other little critters, but they aren't found typically this late on in the Tonian period, and we don't find any in our section now.
Hi, Steve Pickering. You said in your talk that the sediments shouldn't be tectonically disturbed, but my knowledge of the Dalradian is Dalradian slates and a very brittle cleavage and lots of pyrite inclusions. So where's the line between?
Yeah, it's a good point, and I think the further you go back in the geological record, the more of an issue this becomes and the more of an inevitability this becomes. Most things that far back have been through kind of some form of metamorphic mountain building event, and the Dalradian is no exception. It was deformed during the Grampian orogeny, and that means we do have some metamorphism throughout the Dalradian. It's more intense in certain places than others, and in the Argyll region and in the Hebrides, we seem to be sat in this window of quite low green schist facies metamorphic grade, which for the Precambrian is actually pretty good. If you go either northeast or you go into Ireland, you start seeing much higher grades metamorphic mineral assemblages and deformation. And it's possibly something to do with the fact that we're in a massive depot centre, so the sediments are thickest in this part of the Dalradian. And that might have been shielding it from some of the kind of more intense deformation processes.
I have another question from online. Nick has asked, what lay behind the build-up of CO2 that ended these snowball events? Volcanism or biology? Would the latter have been greatly inhibited by the extent of ice cover?
Yeah, I think it was definitely the former. I think it was definitely kind of volcanically inputted CO2. Biological productivity is usually a net sink for carbon dioxide, so it would perhaps work the other way around. But it's a really interesting question about life during the Cryogenian, because as you saw from that phylogenetic tree, it seems that life perhaps for a lot of those crown groups potentially originated during this time. So life was existing somewhere, and people are doing work in Antarctica now, looking at the base of ice sheets or in these kind of puddles you get on the top of ice sheets to look and see kind of how extreme life, what extreme conditions life can persist through.
Thank you very much. Interesting talk. I've read that there might have been Snowball Earth or possibly Slushball Earth with a bit of open water around the tropics. Is that true, and does it matter?
Is that true? There's definitely these kind of two camps, and certain people think that this hard snowball, so ice covering the entire planet, all the way from the poles to the equator, or you have this phenomenon called slushball, where essentially it wasn't kind of ice everywhere. You might have had a open water belt or something like that, and this is how life persisted. I think if you had to ask for my opinion, I probably lean more towards the latter on slushball, but yeah, I think Snowball Earth as a hypothesis and a concept, the term can still stand because we still have a global glaciation, and it still probably look like a snowball from outer space.
I have another question from online. What kind of educational path did you follow to get into this field? The person that asked this question said that they're interested in going in a similar path and would like to take some inspiration.
Oh, that's a nice question. So I did a geology degree at Imperial with some of my friends that sat here today, actually. And then I did a master's in geochemistry, and then contacted a number of different supervisors and about 2 of them replied, and I ended up doing a PhD with one of them. And yeah, so I guess my advice would just be start reaching out to people and contacting people early doors.
Hi, thanks for the presentation. Really excellent presentation. As one of those friends who didn't know exactly what you did, I think it's extremely impressive, the whole thing, and really easily understood. So, as a non-geologist, you showed us elements of, like, proof of the glaciation and the beginning of the cold period. Did you find the same kind of, not obviously the same exact elements, but elements that show the end of the glaciation period? And could that explain as well why the Marinoan was so, do you have any indication why it was so short compared to the earlier Sturtian one?
See, inviting your friends. He doesn't do geology, and it's an annoyingly good question as well. Yeah, so in Scotland we don't have the Marinoan preserved there, which is one of these issues that we've had with either placing it as a Marinoan deposit or a Sturtian deposit. The length of glaciation, the duration of glaciation, Sturtian versus Marinoan is a can of worms, and we can chat about that after, perhaps. That's not me deflection from the question. But yeah, we do see deglaciation, and we see the exit from glaciation in Scotland and in the Dalradian as well. We see these diamictite beds getting thinner and kind of large, like thicker portions of non-glacial sediment between them. So it seems to be waning out towards the top of the Portishead Formation.
Well, my question was related to that one. Yeah. Sorry, I was just following on from that question. You mentioned that the 2 different glacial periods, one of them had iron formation in, and the other one didn't. I was just wondering if there are theories of why that might have been.
Yeah. So this is probably something to do with the duration and the relative durations of them. The Sturtian was really long, 58, 60 million years. The Marinoan, about 10 million years. For these iron formations to form, you have to essentially have an anoxic to reduce iron from iron 3 plus to iron 2 plus. And when it's reduced, it becomes soluble, so it can kind of move in your oceans, and then when it oxidizes, it becomes insoluble and then precipitates as iron formation. So essentially, during your glaciation, there must have been some sort of kind of oxygenation event. So you had anoxic oceans. Maybe when you had some meltback event of the ice, you then it became oxidized because the atmosphere had oxygen in it, but it couldn't cross that ice sheet boundary. And then you had that iron that was held in solution suddenly all precipitate as iron formation. Why it's not in the Marinoan is potentially just because you haven't had long enough for the oceans to become fully anoxic enough, potentially. But it's a really good question, and it's not my research, but a lot of people are looking at this.
Yeah. This one's a bit more about the golden spike and your potential of upgrading your carrot. Is there likely going to be a sort of hesitation to fully assign it until, I guess, things calm down in Ethiopia and they're able to have a proper re-evaluation? And also, when was the last time the geology in Ethiopia was studied in any detail, especially for this sort of sector of research?
Yeah. No, it's a good point. And it has been researched in quite a lot of detail across kind of the early 2010s. There was a group from the States that were going over there on different field campaigns. What I would say is that when the GSSPs are ratified and formally defined, they have to be in place for about 8 years before potentially there's a re-evaluation. If there's something glaringly, obviously wrong with putting it in the Garvellachs, for instance, and that becomes apparent in the next few years, okay, we have to wait a little bit, but we can change that. It's not a kind of, pardon the pun, set in stone thing. So yeah, I wouldn't say that should put us off placing it in the Garvellachs. If anything, it's going to promote more research. These GSSPs actually promote people to do more research. So hopefully, if Ethiopia opens, I'll be the first to be going over there and having a look, because I would love to do some work over there.
Good luck.
Questions, unfortunately.
No, that's great.
But could everybody just give another round of applause to Ellie? Fantastic. I'm going to wrap up. But first, I just want to say a huge thank you for everybody for coming today. A thank you to the Geological Society for organising. Thank you to KTAP for sponsoring. I'm going to do a really quick plug for the Early Career Network. So myself and Ellen are here from the Early Career Network of the Geological Society. It's mostly aimed at young early career geoscientists, or anyone in their first, I shouldn't say young, it's anyone in their first 10 years of their career. But we also help to encourage students to get involved, and anyone who's thinking of studying the geosciences. Will absolutely encourage it. I mean, look at the cool things that you can do. If you don't want to go to Scotland, there's many other areas that are geologically interesting that might be warmer. So if anybody does want to chat, we should be around. And if you want to find us on the Geological Society website or on our LinkedIn, we're always sharing resources, events. We try and organise networking events, and also our early career geoscientists competition annually, which Elias was the proud and very well-deserved winner of last year. Well, actually, it was this year. It was earlier in May. But there's drinks in the library. If anybody does want to stick around, have a chat, even if you just come and chat to your friends. It's a lovely building. Please take advantage of it. But thank you for coming. I've been told that the new series for 2026 is coming, the public lecture series. So just keep an eye on the website, and they will all be published on there as this one was. So please do keep coming along.